Hello, welcome back to Control Systems lectures. We continue with our lecture on modeling in the frequency domain. In the previous class, we had looked at Laplace transform and inverse Laplace transform method for solving ordinary differential equations. And then we introduced Laplace transform theorems and also explained the Laplace transform tables, which we also make use during some of the examples. In the second lecture, we looked at partial fraction expansion and Laplace transform solutions of differential equations using the partial fraction expansion. So we were able to solve for these equations, especially for the, we solved for the denominator. As a matter of fact, we're solving for the denominator of this function using partial fraction expansion. This expression from the Laplace transform is a very important expression which we'll explain later. So first you develop your model in the time domain, you Laplace transform it, and then you arrive at this equation. Then we solve the denominator, the d of s, and this d of s, in solving it you encounter three cases: the case of real and distinct roots, case of real and repeated roots, or the case of complex or imaginary. This equation is referred to as the transfer function of the system, and we are going to cover that after we finish with partial fraction expansion. So in this lecture, I would like to introduce Matlab, and just a brief introduction of Matlab. During the contact sessions, we have some practical hands on Matlab, but so this is how we're going to go through it. When we meet, I will show you how to start Matlab and how to use Matlab to perform partial fraction expansion. And then we will look at transfer function. Please try to get Matlab installed on your laptop and try to do some of the examples I will show here. And when we meet, we can then do these examples using Matlab. So you remember we solved the cases for roots, distinct roots, repeated roots, and here we're going to use Matlab to solve the same problems. So this was the function we had, and then in using Matlab, the first thing you do is open an M file. So you create your M file, that's where you write your code, then you write the following Matlab code. This Matlab code, the dark ones are the code. Anything after the percentage sign is just an explanation, is not part of the code. So clear means this clears all data stored in your workspace. It's always important to start with clear so that any data that is in your workspace does not mess up with your work. It clears it off. Then our numerator is 2. And our denominator is in the factorized form is a polynomial. So we have -1 minus 2, because from this you can see that s is equals to -1 and s is equals to -2. So we put in those values of s from the denominator in the polynomial in a square bracket. Then we have k, p, and k. This is capital K, this is small k, and these are the poles. So what happens here is the syntax is called residue numerator denominator, where numerator is this, denominator is that. And this syntax yields the numerators, poles, and terms. So when you put this in Matlab and you run the code, this is what you get. You will get k equals to -2 and 2. You get your poles equals to -2, -1, and then you get your terms to be 0. So how do you interpret this? You interpret this by then writing your equation f of s is equals to -2 over s plus 2 plus 2 over s plus 1. So this is, if you use partial fraction expansion, remember you say k1 over s plus 1, k2 over s plus 2. So our k1 is actually 2 and our k2 is also 2. You can see that k2 is -2 as a matter of fact. And so now you use the Laplace transform tables and you're able to get your result back in the time domain doing inverse Laplace transform. So if you look at the second case, it was the case of repeated roots. So we have a repeated roots here. And so if you open an M file again and you write the following command, numerator is 2, denominator is s is equals to -1, s is equals to -2, and -2 because it's twice. So we have -1, -2, -2. Then we run again this syntax, and the results will be these values that we have here. And so we can interpret this by saying that minus 2 is this minus 2, and then it means that s is equals to minus 2. So you bring it back to the equation and you have s plus 2, s plus 2, s plus 1. And the numerator will be minus 2, which is minus 2, and then plus 2. So now you have this. Once you have it in this form, you can inverse Laplace transform using the Laplace transform tables to get your f of t in the time domain. And this is the equation for your system. So this is what your system will look like. So this is the end on partial fraction expansion, and we can discuss more when we meet. Then the transfer function, which I said is a very important component. This is how we represent our systems. So you have a system where you have your input and you have your output. So the system is represented in this form, and the transfer function is denoted as g of s. So g of s is c of s over r of s. You see, this is in the time domain, but this is in the complex domain. So you have to Laplace transform the system before you come up with your transfer function. So g of s is c of s over r of s. And the output of the system is thus calculated as c of s is equals to r of s, g of s. So this is your output. So it's r of s multiplied by g of s. Again, if you have it in this form, this is your differential equation that is in the system, or this is the representation of your system. And so your g of s is c of s over r of s, which is given as this value that is in the box, which is a transfer function. So what you have in here is actually your transfer function. So the transfer function g of s is c of s over r of s, which is this quantity. This is how you understand this. You see, r of s, when the arrow goes into the box, whatever comes in get multiplied by whatever is in and is equals to whatever comes out. So r of s multiplied by this whole lot, which is your g of s, is equals to c of s. So you can see that if you put g of r of s here, it will be r of s multiplied by g of s, which is equals to c of s, where this quantity here is your g of s. So let's do one example. Let's say you've given a system in the differential equation form given by this equation dct dc over dt, which is c, where t is in the time function. Time is a function of time, plus 2c equals to r, r also being your input, and it's also a function of time. And we are told that our r of t is a unit step, which means our input is a unit step, and that our initial conditions are 0. So our initial condition will be 0. So in this case, the first step is to take the Laplace transform of both sides of the equations, assuming 0 initial conditions. This makes it very easy. The ddt of ct will just be s, c of s, plus 2, this will be c of s, and this will be equals to r of s. So the transfer function g of s will be given as c of s over r of s. So from here you can find c of s over r of s, and it will give you 1 over s, s plus 2. We are told that our r of t is a unit step, and the unit step is 1, and the Laplace transform of 1 is 1 over s. So now we need to solve this. In order to do that, we have to perform our partial fraction expansion, or we use Matlab to solve. And once we solve this, we will arrive at the result ct is equals to a half minus a half e raised to 2t. So this is your transfer function, and this is how you solve the problem when you have developed your system model and you want to find it back in the time domain. So first, you Laplace transform it into the complex domain. You find your g of s, which is your transfer function, and then you inverse Laplace transform it to the time domain. Okay, thank you very much. This is the end of Introduction to Transfer Function, and we will meet on during the contact sessions. I will discuss a little bit more on transfer function.